Hi, Assalamualaikum and salam sejahtera to all of you. I hope you are doing well. Okay, so we meet again for our new topic in CES513, which is numerical integrations. So for this topic, basically we have two subtopics, which is the trapezoidal rule and the other one is Simpson's rules. So for the Simpson's rules, we have two methods. One is the Simpson's 1/3 rule and the other one is Simpson 3/8 rules. Okay. All right. Integration can be mathematically represented by the equation of 5.1 shown here, where it is an integral of the function fx, as you can see in the red box, with respect to the independent variable x, and it is evaluated from the limits of x equal to a at the bottom and x equal to b. Okay, as you can see here, the function fx inside the red circle is called as integrand. While according to the dictionary definition, to integrate means to bring together as parts into a whole, or to unite and to indicate the total amount. Thus, the meaning of equation for 5.1 is the total value or summation of function fx dx over the range of a to b. And then figure 1 here, representing a graphical manifestation to the concept. Like for functions lying above the x-axis, okay, the integral expressed by equation 5.1 corresponds to the area under the curve of fx. Okay, so it corresponds to this area between A and B. So the process represented here by equation 5.1 and figure 1 is called as definite integration. Next, the figure shown here is the examples of how integration can be used to evaluate areas in engineering applications. For example, for A, figure A, when a surveyor might need to know the area of a field bounded by a meandering stream and two roads. And then for figure B, a water resource engineer might need to know the cross-sectional area of a river, while for C is the example like if a structural engineering wants to know or wants to determine the net force due to a non-uniform wind blowing against the side of a skyscraper. The other example of using numerical integration in engineering is for computing the mean or average value of a function, of a specific function. So for example, for this case, figure shown here, there are infinite number of values in between A and B. So how are we going to determine the mean value or the average value of this function? Is by doing the integration to the function using this formula. Okay, so that is mean equal to the integration of fx dx from A to B divided by B minus A, or the width of the limits. Okay, this formula has hundreds of engineering applications. For example, it can be used to calculate the center of gravity of an irregular objects in mechanical and civil engineering, and it can be also used for calculating the root mean square current in electrical engineering. Okay. Now, Before we proceed to our main objective of this topic, which is numerical integration methods, some further orientation might be helpful for you to study. Okay, figure here provides an overview of the method of the numerical integration methods, and three of the most widely used Newton Cotes formula are discussed in detail. That is trapezoidal rule, Simpson's 1/3 rule, and Simpson's 3/8 rule. All these formulas are designed for cases where the data to be integrated are evenly spaced. Right? Okay, the Newton Cotes formula here are the most common numerical integration methods. They are based on the strategy of replacing a complicated function or tabulated data with an approximating function that is easy to integrate. Like for example here, we have the integration of this function, and then it will be approximated to this function, where the function fn here is a polynomial function equal to a naught plus a1x plus and so on until a n minus 1 and x power of n minus 1. So for the first method in the numerical integration that will be discussed in detail in this chapter is the trapezoidal rule. For the learning outcome of this subtopic, at the end of this lecture, you should be able to 1. Derive the trapezoidal rule of integration covering CO1 and PO2. Number 2 is use the trapezoidal rule of integration to solve engineering problem, also covering CO1 and PO2. The third one is derive the multiple segment trapezoidal rule of integration. And the last one is use the multiple segment trapezoidal rule of integration to solve problems. That is covering CO1 and PO2. Alright, what is trapezoidal rule? It's actually the first of the Newton Cotes closed integration formulas. It corresponds to the case where the polynomial function in the integration formula before this is first order. Okay, as we can see here, the polynomial function is the first order. So a straight line can be represented as this function f1x equal to fa plus fb minus fa divided by b minus a multiplied by x minus a. Okay, so the area under this straight line is an estimate of the integral fx between the limits of a and b. Okay, so that's the integration is this. Right, and the results of the integration is equal to I here in the box, I equal to b minus a multiplied by fa plus fb divided by 2, and that is called as trapezoidal rule. Geometrically, the trapezoidal rule is equivalent to the approximating the area of the trapezoid under the straight line connecting FA and FB as shown in the figure. So it's actually this area. Okay. Therefore, the integral estimate can be represented as I equal to width multiplied by average height. So width here is equal to b minus a, okay, and the average height is equal to FA plus FB divided by 2. So it's a trapezoidal area. All the Newton Cotes closed formula can be expressed in this general format of the equation shown in the purple box. In fact, they only differ with respect to the formulation of the average height. Okay, figure here at the right bottom of the slides is a graphical depiction of the use of single application of trapezoidal rules. Here, this straight line, to approximate the integral of a polynomial function. Okay, that is the polynomial function, the blue line. So when we employ the integral under a straight line segments, this one, to approximate the integral under a curve, okay, this is the actual integral that we want to approximate. We obviously can incur an error that be substantial. So all this can be an error. So an estimate for the local truncation error of a single application of the trapezoidal rule can be determined by using this equation. Okay, the derivation of this equation can be referred to figure 12 in your lecture notes. So truncation error ET equal to -1/12 second derivative of xi multiplied by b minus a power of 3, where xi lies between a and b. Okay, it lies between, like here, from 0 to 0.8. Okay, since xi is arbitrary, the value of xi is arbitrary, one way to find the approximation of second derivative of xi function is by assuming it equal to the average value of the second derivative. So we estimate this, the second derivative of xi equal to the average value of the second derivative fx. So thus, that equation will be this one. Okay, if the function being integrated is linear, then the trapezoidal rule will be exact. But for example, for this case shown in the figure, for function with second or higher order derivative, some error can occur. Now, we look at example 1 for the single application of trapezoidal rule. Okay, the question is, use trapezoidal rule to numerically integrate the function of x equal to 0.2 plus 25x minus 200x squared plus 675x cubed minus 900x power 4 plus 400x power 5. Okay, integrate this function from a equal to 0 to b equal to 0.8. And note that the exact value of the integral can be determined analytically, and the value is 1.640533. Okay, for the solution, the function values when x equal to 0, so function x will equal to 0.2, while for x equal to 0.8, the fx will equal to 0.232. And then we substitute this value into the formula for trapezoidal rule. Okay, we have here I equal to b minus a multiplied by fa plus fb divided by 2. So then we can get the integral of the function equal to 0.1728. Then we can calculate the true error from here, which is equal to true value given from the question minus with the approximate value that we calculated before. So thus the true error is equal to 1.467733. From there, we can determine the absolute relative true error of epsilon t here equal to true error divided by true value, and we will get 89.5% of absolute relative true error. The reason for this large error can be seen from the figure here. Notice that the area under the straight line had neglects a significant portion of the integral lying above the line. That is area under this actual function. So that's why we have a very large significant number of error. Okay, in actual situations, we will not have any foreknowledge of the true value. So we cannot calculate the true error. Alright. So therefore, an approximate error estimate is required. So to obtain this estimate, the function's second derivative over the interval can be computed by differentiating the original function twice to give this equation. Alright. So the average value of the second derivative, here after calculated is equal to negative 60, which can be used to estimate the truncation error. So remember before that we estimate the value of second derivative of the share here equal to the average value of second derivative of the function. Alright. So after calculated, we get the EA or the truncation error equal to 2.56. The average second derivative, this is not necessarily an accurate approximation of the second derivative of she. That's why we denote the error is approximate, EA, okay, rather than ET. Alright. Alright. One way to improve the accuracy of the trapezoidal rule is to divide the integration interval from A to B into a number of segments. For example, here from the left side of the figure, it's a multiple application of the trapezoidal rule. So for A, we divide the integration interval of A to B into two segments. Okay, 1, 2. And then for B, we divide into 3 segments. C divide into 4. And D divide into 5 segments. Okay. And then we apply the method to each segment. Alright. So the areas of individual segments can be added to yield the integral for the entire interval from A to B. And the resulting equations are called multiple applications of the trapezoidal rule. Okay, the next figure, the right side of the slide, is the general format and nomenclature that we'll use to characterize the multiple applications of integral. So there are n plus 1 number of spaces, equal space, with the width of h equal to b minus a divided by n. Alright. Okay, the general form for multiple applications of trapezoidal rule can be seen here. in the box I equal to b minus a, which is the width of the space, and multiply by fx naught plus the summation of fxi multiplied by 2 plus by fxn divided by 2n. That is actually the average height of the integration or the trapezoidal. So an error of the multiple application trapezoidal rule can be obtained by summing the individual errors for each segment, okay, to give this equation. Where the second derivative of xi is the second derivative at point xi located in the segment I. Okay. This result can be simplified by estimating the mean or the average value of the second derivative for the entire interval. So that is the mean of the entire interval. Therefore, the error can be written as this: EA equal to negative b minus a power of 3 divided by 12n square multiplied by the average value of the entire interval. Note that the equation is an approximate error because of the nature of this. It's an approximation, so that's why we use EA. Let us look at example 2 for the multiple application of trapezoidal rules. Use the two-segment trapezoidal rule to estimate the integral of fx equal to 0.2 plus 25x minus 200x squared plus 675x power of 3 minus 900x power of 4 plus 400x power of 5 from a equal to 0 to b equal to 8, and estimate for the error. Recall that the correct value of the integral is given as 1.640533. So for the solution, okay, we consider n equal to 2 and h equal to 0.4, because h is equal to b minus a divided by n. Alright, so for fx0 is equal to 0.2 and fx equal to 0.4 is 2.4656 and f0.8 is 0.232. Okay, substitute all the values into the formulation of multiple application of trapezoidal rule. Then we will get the integration value of 1.0688. From there, we can determine the true error and the absolute relative true error of 34.9%. Alright, and then we can estimate the truncation error using the formula given in the previous slides, which is equal to b minus a power of 3 divided by 12n square multiplied by the average value or the mean value of the entire integrals. So that we get 0.64. Note here the negative 60 is obtained from the previous example, in example 1. Okay, table here is the results of multiple application trapezoidal rule to estimate the integral of function x in the example 2. So the function is integrate from x equal to 0 to x equal to 0.8. Notice how the error is decreased from 34.9% to 1.6 as the number of segments increase from 2 to 10. Alright. Also notice that the rate of decrease is gradual. So this is because the error is inversely related to the square of n if we see from the previous formulation. Okay. So that's all for subtopic 5.1, which is trapezoidal rule. You can look and try to do other example in the lecture notes, and there is one exercise that you can do to test your understanding in this subtopic. All right, thank you very much.